maybe we're ready to start. So,
Yep,
okay.
online.
Okay,
I'll,
good.
I'll I'll grab a link and put it in chat for people.
All right, good. Yeah, so Shamash will be streaming us live to YouTube as well, and then there'll be either that will stay or he'll put something up later on in the Scientific Discourse channel on YouTube where we're collecting these things now. So another thing to look at, maybe put in the chat too if you get a chance, Shamash, if you haven't already. I think you haven't. So let me invite anybody who wants to come up on stage and be here. I always like I've got a good crew who will keep me honest, but if anybody else wants to be up here so that they can actually chime in as opposed to putting things in the chat, which I may or may not see in a timely manner, raise your hand and we'll bring you up as well. There's Benjamin. Good to see you, Benjamin.
Morning.
Morning. So let's, if you open the slides at the top, we're going to talk about resonance phenomena today. It has crept into other bites of physics in the past, as it really has to, because resonance is everywhere. I kind of hope to convince you to look at the world through resonance eyes when you're done, because it's kind of one of the fundamental things that make the world go round. Let's just leave it at that. So if you open that up, you'll see we are doing Bite of Physics number 71. There's links to all of the previous Bites of Physics and some Nibbles of Physics, which was kind of an aborted series, I think. I may do some more of those at some point. And then lots of public documents that I just keep making little treatises on various things. So if you have no life at all, you might click on that and check things out. If you go on to slide 2, we'll just start by talking about states of systems first and distinguishing between equilibrium states, distinguishing equilibrium states in particular, because that's important. So when a system is in an equilibrium state, there's no net force making that state change. And you should wonder what a system is, what's a state, what's a force. I don't intend right here to go into any detail there, but a system is a well-defined bunch of stuff, and a state is something that describes the configuration. That's probably the best way to say it, of that stuff. Where that stuff is, where all the stuff is right now, where it is in relation to other parts of the system, other stuff in the system, etc. And what's a force? Well, we kind of feel like we know what forces are, but they can be a little abstract too in some cases. A force is any kind of a physical influence that can change the state of a system. And so almost by definition, if a system is in an equilibrium state, there must be no net force. Net's kind of important because sometimes you can have lots of forces, but they oppose each other in such a way to make no net force happen. There's no net force because it's in an equilibrium state. If it couldn't be in an equilibrium state if one of these forces, which will change the state, was operative. So that's all pretty simple, almost tautological, I guess. Equilibrium states are further subcategorized as stable, neutral, or unstable, depending on the nature of the forces that might arise if the system is perturbed from that equilibrium state. And the diagrams that I have there are kind of the canonical way in which we describe them. We often think of it in terms of energy. If you think about a ball in a bowl, the equilibrium state of that ball is to be at the bottom of the bowl. There's no net force on it at that point. But if you perturb the ball in any direction from that equilibrium state, forces arise that try to push it back to the equilibrium state. And you might think about what happens if you just perturb it to the side and let it go. I think immediately you'll see that you'll get some oscillations around that equilibrium state, and that's what we're going to be moving into next. But the most important thing for right now is that there's a force that pushes it back. If that ball was in a bowl full of honey, it might take a very long time to get back to the equilibrium state, and it probably wouldn't oscillate. And so that's another important thing, the idea of damping that we're going to talk about as well. The second figure shows a ball at a kind of at a high point on the top of a bowl or on the top of another ball or whatever. If you perturb that ball from its equilibrium state, forces arise that try to push it further from the equilibrium state. There can be no oscillation in this case because the forces simply move it further away, and that's that. It won't come back. It certainly won't oscillate around that state. And then the third one is just the case of a ball on a flat part of a track. You can think of a roller coaster on a flat part or whatever. In that case, if you move it a little bit one way or the other, actually, I shouldn't. I'm sorry. It isn't. I just realized I probably clipped the wrong drawing. I meant to have a drawing of a ball on a level part of a track. I don't know. I'm not sure why they didn't do it that way. But if it were a level part of the track, then you could move it a little bit one way or the other, and there would be no force at all if the track were really level. Of course, if you move it a little further, you might encounter either an unstable kind of a thing or a stable. So this is really, rather than what the diagram says, it's an example of something where it's basically neutral equilibrium where it is. You can move it a little bit and nothing will happen at all. But if you move it to the right, then it's going to be returned and then go, of course, because it gets returned to that point with some speed, it will probably just go on off the left side all by itself. So my bad. I should have spent more time picking my diagram there. Any comments or questions on that? There's lots of things this leads to, and we will get to many of them. But any burning comments at the moment?
Not sure if you want to get to this here or not, but are we going to talk about the definitions in great detail, or are you going to just brush over it and move on?
The definitions of system, state, and force, you mean in particular?
Yeah, because it sounds to me like there's some circularity. So the rest state or the equilibrium state is defined by there is no net force that's making it change. What's a force? It's whatever makes the equilibrium change.
Yeah, it is, I think, a little circular in that sense. Certainly in some of the simple cases we're going to talk about, it won't seem so circular once you really see the source of the force, but I agree with you. Okay, well, let's move on. Let's move on to slide 3, where I just want to end it, and I'm really glad Sam is here for this because this is a lot of what goes on in chemistry. Here's an example, if you want to think of it, a ball on a track that starts off at the left high, coming down to a local minimum, and then going back up to a high peak, and then coming back down to another local minimum that appears to be, at least for the part of the track that's being seen, the lowest point there is. Now, both of those points that are called metastable and stable, I would call a stable equilibrium. But this gets at the point that the nature of an equilibrium does depend a little bit on just how much you displace it from the equilibrium. That metastable point is a point that is a stable equilibrium as long as you don't perturb it too far. If you perturb it far enough, then it won't come back to that place. It will roll on down, and if there's any kind of damping in the system to reduce the total energy, it will end up then presumably at the lower point. Sam, do you have a few words to say about metastability? Sam may be busy, but this is a big part of chemistry, and I'm going to return to it on the next slide very briefly. So just to kind of indicate these states again, there's a diagram over on the right that shows now a genuinely neutral, stable situation, a ball on a table. You can displace that ball a little bit. It's just as happy to sit over there as it is where it's sitting right now. No force tries to either push it back or to push it further away. The the middle is a diagram, the stable equilibrium. That's a nice graph for a stable equilibrium, but I would argue that the picture up above is an example of what a good example of meta stability. If you push that object a little bit, maybe as much as is being shown, and then release it, it'll wobble around in kind of a funny way, right? It's a very jerky kind of an oscillation in a situation like that, but it'll come back to the stable equilibrium where it's standing straight up. But of course, if you push it too far, it says, "Oh, there's an even more stable state I can find at a lower amount of energy if I sit on my side on this table." And strangely, of course, that new quote stable state really isn't stable because a cylinder like that can roll along the table in a neutral equilibrium kind of a way. So you see, I like that example because I think it really illustrates that the stability, metastability, instability, neutral stability of a system depends a lot on what specific kind of perturbation you're talking about, how much perturbation, etc. And then it shows finally on the far right a pen kind of a thing. I think it's like a Marx-a-lot or something. Presumably it has a kind of a sharp tip that you could, at least in theory, balance on that tip, and it would be in equilibrium, but it's a terribly unstable equilibrium because even a breath of air would presumably make it fall over into that same kind of weird neutral stability that a cylinder has rolling on a table, etc. So, any comments on that?
I love this example, and I probably done it a million times, but never thought of it that way.
Yeah, that's exactly the kind of reaction I hope to stimulate with a lot of the things we're going to talk about today. Is just looking at the world kind of with different eyes and seeing these phenomena over and over. They're just everywhere in front of you if you learn to look at the world that way.
I would just add that in like parallels to this, or in machine learning, you talk about things like local minima. If Sam was able to speak, I'm sure he'd pipe up and talk about activation energies in chemistry. So all these other familiar concepts.
That's right. Yeah.
Local stability, another word you might hear in another field. So all these types of things are very similar.
Yeah. So let's go on to slide 4. A few quick examples of stable equilibrium. I've got some pictures of some of them. A mass on a spring. That's a really simple example. And I want to emphasize that it's simple, especially the way we deal with it in physics, is we think of it as a particle, a single particle. Yeah, it really is a block, and that block is made of atoms, and they have lots of jiggly things going on. But we really think of it as just a particle on a spring. And to the extent that you think of it that way, it has exactly one thing to think about: how much that spring is compressed. I'm not going to worry about the mass maybe rotating out of the plane of that page or leaving the plane. I'm thinking about the plane being frictionless, but maybe not, right? It can put some damping in if I put some on that plane, but it's pretty obvious right now that the idea here is that if I pull that mass to the right and let it go, it's going to oscillate. And we're not thinking about the fact that oscillation is a little weird because the spring maybe will pooch out when it compresses. And what does that do? Does that end up pushing the mass off to the left or the right? All sorts of complicated things can happen, but we really just want to, we think of it in one-dimensional motion, thinking about something that keeps both the spring and the mass always in the plane of that page. Oscillating back and forth. We do what a physicist always does and don't worry about the complications at first. Maybe we get to them later. So that's a mass on a spring. We can have several masses connected by springs, and the immediate difference, as we'll see, is that in the first case, there really is one obvious kind of oscillation that can happen, and that oscillation has a frequency. We're going to see that when you get to more complicated systems made of many things that can move relative to each other, may be connected by spring-like forces. that now lots of things can happen. In the second case there with the three masses connected by four springs, um, even if I simplify it by saying let's just assume that those masses stay in the plane that they're in, stay in that one-dimensional line, then I can kind of push all the masses to one side and let them go, and they'll kind of oscillate back and forth, kind of like one mass, not exactly as it turns out, but kind of like one mass. Well, actually, I think it is exactly now that I think about it. But it can oscillate back and forth like one mass. You could leave the middle mass where it is, move the two masses on the side toward each other, and then let them go. And you'd have another kind of an oscillation where the mass in the middle just never moves. The masses on the sides move back and forth in opposite directions all the time. And there is one other mode for a situation like this of oscillation that I'll just leave you to think about for a moment. Let's see. So, does anybody want to add anything, or maybe guess what that third mode of oscillation would be? And I'm using some words here when I say that. We're going to talk about what are called normal modes. These are modes that are repeating. There are three ways, it turns out, that those three masses connected by four springs can oscillate along that one dimension in which the pattern of oscillation repeats at a constant frequency in a very simple manner. And I've told you two of them, all three masses going side to side, one with the middle mass in the middle and the other two going in opposite directions. And there's a third one as well. But any comments on any of that? Maybe I'll give you another chance here when we finish the page. So let's talk about the rest of the page here first. So atoms in a molecule are another good example. I show a couple pictures of the water molecule over there. One that's a more quantum realistic view where the oxygen atom is kind of this fuzzy ball of electrons that's merging with a couple of fuzzy balls of electrons around hydrogen nuclei, and then another one that's more of a ball and stick model of the hydrogen molecule. But whichever way you look at it, it is the case that that system has a kind of an equilibrium where the two hydrogens make a definite angle. There's a definite angle, and I can't remember what it is. Sam, if he's there, could tell me probably immediately.
108, if I remember correctly.
Is it 108? Okay.
It's less than 120 because there's a difference in potential between the hydrogens and oxygens. I'll Google it to make sure.
Yeah. Sam knows. Yeah, Sam, what do you got for us?
Yeah, 107.5.
Oh, you're very low, Sam. I'm not sure. Your mic is low.
Is it better?
That's better.
Yeah. So I think it's 107.5 in water.
Oh, okay, good. So Shamash, you were wrong. It was 107.5.
Damn it.
And those take grades.
Okay, and then of course the point is that molecule can oscillate around that. It can oscillate in lots of different ways, because there are three things like there were in the example above, but also because really in reality the thing can oscillate in two dimensions at least, as opposed to the one dimension. You might wonder about oscillating in a third dimension. That brings up other topics as well. But I'm not going to go further into that right now. We've already talked. Yeah, go ahead.
If I could interrupt you really quickly. So I'm really glad you're giving this lecture now, because on Monday I'm going to do a review in my chemistry, but then next Monday after that I'm going to start with the thermodynamics lecture, which starts here. So basically,
good.
What you're doing,
Slide 4.
You're giving the theoretical basis for my room in a week and a half.
Well,
And
good.
so this is awesome.
All right. Well, that's good. Let's see. All right, so moving on, ball in a bowl we've already talked about. Plumb bob, I've got a picture there of a plumb bob, just a weight, usually a pointed weight, so that it points at a definite place on the ground when it's not oscillating like a pendulum, because a plumb bob is really just a pendulum in its equilibrium state. So there's a picture of a plumb bob, a taut string, and put the next example there. That ball hanging, that kind of silvery ball hanging from a string, somehow from the red ball. I don't know what that apparatus is, but I kind of like it because it's both a pendulum, it's a plumb bob without a point on the bottom, and it's also got a taut string there. So when I ask what kind of ways can that thing oscillate, you might think about the pendulum mode, but I could also set up an oscillation in that string from the red ball down to the silver ball hanging from it, because that string is tight, and if I displace that string from its straight line equilibrium state, there'll be oscillations. They won't just be a thing moving back and forth. It'll be a whole string with parts of the string moving in one way and parts of the string moving in another way. And it just gets complicated. I'll just leave it at that for now. We'll return to that at least briefly in the soon. And a bell. A bell is a really interesting example, a complicated system of lots of stuff that has lots of different ways it can vibrate. In
especially with
fact,
that crack in it.
especially, well, lots of complicated ways that it can vibrate because of the crack, but probably no more ways that it can vibrate. The number of ways it can vibrate, might be something like the number of atoms in the bell. If you extrapolate from the masses on the spring thing, a single mass on a spring kind of has one way it can oscillate. Three masses on those springs there have three ways. We've talked about two of them. I've still got a challenge out there for what the third one is. That bell is composed of, something on the order of 10 to the 25th or 10 to the 26th things that are connected to each other by springs, if you want. And so at some level, there's something like 10 to the 25th or 10 to the 26th different ways that bell can oscillate. Only maybe 20 or 30 of them that we actually care about. And I'm going to return to that example in later on. And then I put one there just kind of tantalizing for Benjamin, I guess, more than anything else. Electrons in the wire of an LC circuit. That's a circuit that has an inductor and a capacitor in it. And I don't want to talk about that any further now, but we might talk about that in the discussion later on. So I'm
John,
done
with
with
these
this slide.
modes of vibration, which ones have you mentioned? Sorry, you said all moving
So
together. So
yeah,
the
all together, and then
first
one in
mode.
which the middle one is stationary, while the two outer ones oscillate in opposite directions.
Okay, and then
So what is the third so-called normal mode? I'm getting ahead of myself, but way in which this system can vibrate such that it repeats the oscillation every time it comes back to the initial configuration.
well, can't they do the next? So they can they not go into into a mode where they go in and out of phase, the outers compared to the central?
Meaning
So,
what?
well, the outer masses move opposite to each other,
Hmm.
while the middle one just kind of does the opposite to what they're doing effectively. So the
So
opposite, the outers are
what would
going
the opposite be if they're doing something that's opposite each other?
well toward. So at one point, the middle mass goes towards, say, the right hand, and then and the next cycle, the middle one moves towards the left hand, and then that cycle repeats. So it's a pattern that repeats
You're
itself
kind of
every other cycle, if you like.
Yeah, so you're kind of halfway there. You've got what the middle mass does, right? But I think you're still conflating it with the second mode. In the third mode, mass one and three move identically, while mass two moves opposite what they're doing.
Yeah, yes. So identically, when viewed from the outside, right? So you're saying that masses 1 and 3, when you look at it from outside, they are just either moving left together or right together. Is that what you're saying?
Oh, right. Maybe that's what you meant to say from
No,
a
no, not
different
necessarily.
viewpoint.
I'm just trying to work out what you're saying. So you're saying that
That's
1
right.
and 3 go left and right together, And
Right.
whatever they're doing, the middle mass is doing the opposite as viewed from the outside.
Yeah, that's right.
Okay. Yeah,
That's
cool.
right. And maybe just a quick think about those again. When the masses are all moving together, the middle springs kind of aren't doing anything, right? It's really just the first and fourth springs that are actually doing anything. When the mass in the middle stays where it is, the two masses, the mass 1 and mass 3, are moving opposite each other. Then all springs are doing something, but what they're basically doing is just kind of the first and second springs are operating on mass 1, and the third and fourth are operating on mass 3, and keeping mass 2 where it is. Whereas in that third mode, where mass 1 and mass 2 move to the right while mass 2 moves to the left, you can see that that causes just, first of all, they're all involved. And second of all, the springs are being as radically compressed or stretched as they can be. So you're getting a lot more spring involvement in that motion. I don't know. To solve this mathematically. It's easy to solve mathematically for what happens, but it does require differential equations and everything like that. And I don't know that it's easy to see intuitively, other than just to kind of see the massive involvement of the springs in that third mode. But I'm getting way too far ahead of myself. Let's move on to slide 5. Couple of examples of neutral equilibrium. Ball on a table, we've already kind of talked about. Rope on the ground, right? I could change that rope. I could move it around, and it would be just as happy sitting on that ground in any other configuration. But I did put a question mark there, because it is the case that, at least to some extent, if I just try to kind of bend a little piece of the rope and then put it on the ground, that rope may kind of try to come back to its length. It doesn't. Ropes don't like being bent too much. They kind of resist being bent into sharp hairpin turns, just because of some internal forces that they like being straighter. Of course, some ropes, if they've been abused, like being curved in a particular way too, but they have some memory of their configuration that way. So this is all just to say it's a little complicated, right? It's not just, you can't just take that rope and lay it on the ground in any configuration. If you do, it'll probably self straighten or self curve. Right? Badly abused. I have a lot of mic cables that have been abused over the years, and they can't be straightened anymore. That memory effect. And then same idea for the pile of blocks. I put that pile of blocks on the floor. I claim I could put that pile of blocks on the floor in lots of different ways. There's nothing particularly stable about the equilibrium, but on the other hand, it is kind of stable, because if I just touch one of those blocks, it's probably going to come back to where it is. This puts us in mind of Jenga, right? Jenga's kind of a meta-stable thing. You can touch things a little bit and they'll return to their equilibrium. So it's stable for tiny little perturbations, but maybe not stable for larger perturbations. And all of that is just to say this this topic is complicated, but it's made at least, but it unifies it with lots of things if you think in terms of stability and metastability and instability and all of that kind of thing. Okay. So let's do 6, and then we'll stop again. So unstable equilibrium. Here's a couple of examples. Ball on top of another ball. Stable, but probably you'd have a hard time getting it to stay that way, at least in theory stable. I use the example here of a mass between two compressed springs. That's a stable equilibrium, and if you really confine the mass only to move along that line, then I guess you'd say it's really stable. But of course, any real mass on a table between two compressed springs is probably going to pooch out to the side, unless you get it exactly between the two springs, or unless you get some help from friction from the table. These are all just kind of intuitive concepts that I'm hoping to draw on. So questions about any, or comments on any of that? Or kind of move into resonant modes next. Okay, let's go on to slide 7. Slide 7, I just point out that stable equilibria have associated with them natural frequencies of oscillation. Those frequencies are always associated with a couple of parameters, one that has to do with stiffness and one that has to do with inertia. And it's an amazingly common situation. You find this. It's always the case that when you have this kind of a thing, that the natural frequency of oscillation will be, because of the solution of a differential equation that describes these things, the square root of some stiffness parameter divided by, of the stiffness parameter divided by the inertia parameter. This is a really remarkable and kind of universal feature of these things, as long as you're talking about small oscillations around a stable equilibrium. It's not, I said universal, it turns out it's actually not universal, but it's almost universal. So that
John,
makes it
in that
universal.
simple pendulum example there, it doesn't seem right that it's 2 pi root g over L. If you increase the length, the
Oops.
frequency, is that
You're
right?
right. You're
Oh, no, hold on, no,
no, no,
period.
no,
You've got
no,
frequency.
frequency.
Frequency, not
Frequency.
period. Okay, thanks.
Thank you.
So
You,
just,
you
yeah.
had me going too,
No,
Ben.
yeah, I was just common
Immediately.
sense checking it, but it's frequency,
Yeah.
not period. You're good.
That's right. No, but you did have me going too. It's important that we're talking about frequencies here. And so, in the case of the mass on a spring, the stiffness constant is a thing we call the spring constant. And the spring constant is kind of a natural thing, I think. You think it's how much force the spring exerts for a given amount of stretch. It's measured in newtons per meter or pounds per foot or something like that. How many pounds of force it will exert on you if you compress it by a foot. And maybe you can't compress it by a foot, but you can compress it by a tenth of a foot, and you'll get a tenth of those numbers of pounds, etc. So it's the competition between the stiffness of the spring, measured in newtons per meter, and the mass on the end of the spring in mass. And one of the other remarkable things is that if you actually work that out, a newton is a kilogram meter per second squared. So a Newton divided by a meter is a kilogram per second squared, whatever that means. So a spring constant can be measured in units of kilograms per second squared. And I challenge you to, make sense of what that even means. But when you divide that by kilogram, you just get per second squared, and that's the units of frequency, something per second squared. And if you want to get cycles per second squared, which we typically do when we talk about frequency, then it turns out you have to multiply that thing by 2 pi, because the natural units of frequency are actually radians per second, which is a weird thing, whatever that is. I don't want to talk about it. The frequency is 2 pi times the square root of k over m, the stiffness parameter divided by the inertia parameter. In the case of a simple pendulum, the stiffness parameter is the gravitational field strength. That's the thing that makes it want to return. And the thing that resists that desire to return is really the length of the pendulum. Now, you might not like that. You might like to say, well, isn't the stiffness thing really just the weight on the end? And isn't the inertia thing really also kind of related to the weight? And I would say, okay, that's fine. So make it be the weight and make the inertia parameter be not really the weight, but the weight and the length of the string, because you can see that the longer the string is, the harder, a given force isn't going to be as effective. This has to do with torque. Maybe I won't claim that to be intuitively obvious, but if you think about it for a while, you'll start to see that. And in either case, you can think of that frequency formula as being 2 pi mg divided by ml, and then the m's just go away. Or you can just take my word for it that the stiffness parameter is just the gravitational field strength, and the inertia parameter is just the length. This has to do with the fact that mass appears in both of those things, and that has to do with what's called the equivalence principle. And the equivalence principle is kind of the basis for general relativity, and we could just go on and on and on. But the nice thing about the frequency of a pendulum is it doesn't depend on the mass of the pendulum. It just depends on the length. and where you're doing it on the Earth, supposedly. And all of these are for small oscillations. If I move a pendulum, if I let a pendulum oscillate through a larger amplitude, you actually find out that the frequency gets a little smaller because of the nature of the pendulum, because of the fact that it is confining the object to move along a circular path that makes the oscillation take a longer and longer time. The Yeah, that's right. The longer time meaning a smaller frequency. I think I said all that right. As you make the amplitude larger, but that's a nicety we don't have to worry about here, except to say that all of the stuff we're talking about is complicated. And one of the complications is that things do depend on the amplitude of the oscillation. So I've said too much about that. Any comments? Ben,
Did you
did you
say
have
whether
some?
the mass on the springs frequency depends on the size of the oscillation as long as it's
Oh,
small?
yeah, thank you. I did want to say that it also does, right? And I don't know, were you going somewhere in particular? Because why don't you take it, Ben, if you
No,
want?
no, I was just gonna put that point in. That's all. You talked about the length
Okay.
and the size of the oscillations with the pendulum, but I didn't. Yeah.
Yeah. So in the case of the spring, of course, it's a little less obvious why you have to keep the oscillation small, but you do because if you perturb the spring too much, perturb the mass too much, you just destroy your spring, and then it doesn't do what it was going to do for
Okay,
smaller
so I
oscillations.
guess the angle I was coming at though is provided the oscillations with the spring are air quotes small, it doesn't matter what the size of the oscillation is, you still get the same frequency, right? As long as you don't
Yeah,
come out of
that's
that
right.
regime.
In the case of the mass and the spring, it's to a pretty good, to at least as good as we probably ever care to talk about it. As long as you don't permanently deform the spring, go beyond what's called the elastic limit of the spring, then the spring has this really nice property that it really does exert a force that is proportional to the displacement. And that's what's important. What turns out to be important is that the return force is directly proportional to how far you are from equilibrium. And a spring does a really good job of that as long as you don't deform it too much.
And as Gokul has put in the chat, thank you, Gokul, he's saying, basically as long as it is linearly elastic, I think is a reasonable way of
Right.
saying it.
Yeah,
And
exactly.
and another reason this could be important is if you wanted to derive the mass of something in microgravity in space, then this could be a way to do it, right? You put the thing on a
Right.
spring, you oscillated a small amount that's nowhere near the threshold of nonlinearity, and then you just look at the frequency and that tells you the mass. You can see that from your equation there. It only depends on the
Right.
spring constant, which shouldn't change going into space, but you're going to want to watch the temperature and the history of the spring and a whole bunch of other stuff, and the mass. So it's another way of weighing things when there's no gravity.
Right, and I think they do that. As I understand it, they kind of have a scale on the International Space Station, which of course doesn't measure the weight of the astronauts because the astronauts do have no weight, but they do still have mass, and it uses. And as I understand it, it kind of uses that. They kind of put the astronauts in a little chair on a or something,
Yeah, and
with a
there's at least
spring on
another
them.
couple of ways you could weigh things in space. Of course, you could. Well, there's at least another couple. You could put them in a centrifuge and spin the centrifuge at a known speed, or just put a known mass in a centrifuge with a scale and see what the scale reads when you spin the centrifuge up, and then put your unknown mass in and just use the ratio. So you could do that,
That's
centrifuge
right.
and a scale. I mean, another thing you could do, and this is straight out of the book, brilliant book, by the way. It's written by the author of The Martian, Andy Weir, and it's called, what the hell's it called? Project Hail Mary. In there, he concocts the idea of weighing something by, this is quite clever, taking a known mass. This basically creates a balance in space, right? So he takes two little cups and a piece of string,
Mm-hmm.
and
And
he
pulls
ties the
on
two
it.
cups together. Not quite. No, ties the two cups together, um, bends the string so that it marks the halfway point, so he knows exactly where the halfway point is with like a pen.
Mm.
And then he can put a known mass in one bucket
Mm-hmm.
and the unknown mass in the other, and then spin it. And if it spins around anything but the center point, then they're different masses. So now he's got himself a balance where if he keeps adjusting the known mass, then eventually he can match and it'll spin around its precise center point. And now you've got, what
Oh.
the mass is. You said, can you
Oh,
imagine
that's
that?
nice. That's
Yeah,
nice.
pretty
Yeah.
cool.
Right.
So it's just like
Yeah.
literally creating the equivalent of a baker's balance on Earth, but by spinning things in space.
Right, and all of them relying on what you call in Newtonian mechanics fictitious forces in order to replace the fact that you don't have the fictitious force of gravity to to use to get the mass. But that's
Fictitious
another.
force now. Oh my God.
I knew that would get a rise from
Don't give him
Benjamin.
ammunition, John. Careful.
Okay, so let's move on to
Can
eight.
I very
Yeah,
quickly before we
go
move
ahead,
on?
Shamash.
I think the frequency should be 1/2 pi the square root, and not 2 pi times the square root.
Oh, you are
I'm
correct.
kind of doing the
Thank you,
math now, and the
Shamash.
period starts with 2 pi, right? So it's one
Thank
over the
you.
frequency. Yeah, okay.
Oh,
I'll fix it.
thanks, Shamash. I knew something was wrong with it, but it wasn't
Yep.
what I said was wrong with it.
No, you're right. And so I am correcting that as we speak here. Let's see if you, next time you refresh that page, hopefully it'll show the right thing. Let's see. Okay. Yeah, good.
That's
Yeah,
far,
thank you,
yeah.
Shamash. I just knee jerk put that 2 pi in there without thinking about it. Okay, let's move on to slide 8. So more complicated systems can have, as we've already seen with the three masses on the string, more many natural frequencies. And a string is once again kind of like the bell, a really complicated system. It consists of lots and lots and lots of little masses that are all connected to each other, so it can oscillate in lots of different ways. And just like we did with the masses, we can talk about the so-called normal modes of oscillation, which for a guitar string have to do with the fact that the ends of the string are fixed at at one end of the nut and the bridge. And then the string can oscillate kind of up and down in that kind of most obvious mode. But it can also oscillate in a mode where the middle of the string doesn't move at all. And it kind of oscillates oppositely on each side of that. It can oscillate in a mode where there's two places that don't oscillate at all. One third of the way from the right end, and one 2/3 of the way from the right end. And then you've got opposite things going on one side to the other there. And this should harken back, if you were there for the quantum mechanics series when we talked about solutions of the Schrodinger equation, when we had multiple potential wells. We had a very similar thing to this going on when it was really important to think about how many nodes the solution to the Schrodinger equation had. It's very closely related to what we're talking about here. And of course, that series that shows the first 4 normal modes there for the guitar string just continues on. It just gets really hard to actually see, or to see the modes at higher frequencies. And I should mention one other thing about a guitar string. This is all based on the idea that a guitar string just has a tension that returns it to the equilibrium because it's being pulled on at each end. But there's another thing that goes on with guitar strings, or any kind of string, especially metal strings, and that is that the metal string just wants to be straight. Doesn't even have to be pulled at the ends. It wants to be straight. And when you talk about higher modes of oscillation where the string is curving very quickly, notice it doesn't have to curve very quickly in the first mode. But as you go to higher and higher modes, it's curving really quickly. And in addition to the tension force that wants to return it, there's just an internal stiffness force that makes it want to return. And the net result of that is that the higher modes of oscillations are actually at higher frequencies than you would expect, just given the tension, which is the stiffness parameter here. And that causes harmonic problems musically, because the nice thing about a guitar string is that the frequencies associated with these modes are harmonically related. They make pleasing music. The problem is that at higher modes, those frequencies are no longer harmonically related. That's not much of a problem for guitar strings, but it's a really big problem for the low frequency strings of a piano, which are really thick and really stiff. They want to oscillate at a higher frequency, even if they're not pulled taut to begin with. And once again, I'm diverging a little bit from the main topic, but it's just that's kind of an interesting thing and it has lots of ramifications in piano tuning that some of you may be aware of. Let me just,
There's
yeah, go ahead.
sorry, yeah. There's also the problem when you have thick and very tight strings, that the torsion on the strings, because they are wound most of the time. So that torsion, as they are wound with other metal as well, it creates that force that wants to untangle the thing a little bit, and it becomes very resistant to manipulation.
The twisting torsion, you mean
Yeah, yeah,
twisting
yeah.
of the string? Yeah, that's right. So as it oscillates and gets longer, there's a, yeah, right, there's a bit of a
I suffer
torsional
from
effect.
this as I fix the new strings on my instrument, because I'm very aware that I don't want to twist it in the same direction as it is wound, so that to amplify the problem. So I want to kind of give it an opposite twist and then fix the string.
Oh, interesting. And we're gonna have to talk about that. I don't know that
We will make a music
yeah.
theory room. I'm dying for it. I've been thinking about it the other week. We shall do it at some point.
Yeah, good. And so on this page, I also then have the much more complicated normal modes of a bell. Bells are really interesting things because the fact that they're three-dimensional objects that you bang at, so you hit it someplace, and in the process of hitting it someplace, you stimulate different amounts of these normal modes. Very complicated topic itself. But what are they? The lowest modes of a bell have to do with it oscillating in such a way that the entire bell kind of compresses in one direction and elongates in the other. So that's what it's showing here. There are, if you imagine this bell being, suppose take that top left picture there, the hum tone as it's called. This is the bell where the left and right side move outward from each other while the front and back move toward each other. And then on the opposite phase of that oscillation, the front and back move away from each other, the left and right move toward each other. And in the process of doing that, there's a couple of lines across the bell at 45 degrees to front and back that don't move at all. Those are the nodal lines on the bell, and that's what the diagram is showing. Nodal lines at 45 degrees, well, 90 degrees to each other, 45 degrees to the where the bell pooches out. So they've got the bell kind of pooching out at 45 degrees in those two oscillations, or those two pictures. Pooching out in one direction and then pooching out in the other direction. That's the lowest frequency mode because it's the kind of least complicated, least bendy mode, if you want, the hum tone of a bell. And then the prime tone of the bell is just like that, except in addition, rather than just doing that for the whole bell, what happens is the lower part of the bell goes in. So looking at that picture at the top right, the sides of the bell move toward each other at the lower part of the bell, while in the upper part they're moving away from each other. And that leaves, in addition to the nodal lines we had before, there's a nodal circle defining the difference between the part of the bell that's going out when the lower part is going in, etc. And if you look at the rest of these diagrams, the nice thing about the nodal line way of thinking about it is it kind of immediately tells you what's happening in each sector. The opposite, adjacent sectors are always doing the opposite. So the so-called tierce mode there apparently also has one nodal line, but it's at a different place than the prime tone. All of this stuff was worked out kind of in an empirical fashion from the need to make bells that sounded musically like they were playing a tone. A bell, a three-dimensional object like that, just doesn't do that very well because you strike it and you get a bunch of different frequencies that are not harmonically related. But by fashioning the bell into the right shape, putting enough weight around the skirt at the bottom, having it pooch out in just the right way, having the shape be just right, you can you can manipulate the frequencies, and so that they come into some kind of a musical relationship. You can't get all of them, but if you get some of the lower frequencies to be like twice each other, or 50%, 1.5 times each other. These are all musical relationships that make the bell, so that you can actually then put a carillon up and play a tune, and people will at least recognize the tune, even though it is clangorous, meaning kind of dissonant musically. There are dissonant things going on, but there's still some harmonically related things that make it sound good. Maybe enough said about that. Bells are complicated, but we manipulate them to try to make those normal modes musical. Anything on that?
It just that church bells always annoyed me, and now I discovered that it's not because they're old; it's because it's impossible to tune them. I always thought it's like, it was such a lazy dude. Like, the guy who tuned it probably doesn't know music. Oh my God, they're so annoying. And now you tell me, oh no, he can't do anything
You
about it.
can't do it
Okay.
anyway.
Yeah.
Yep. Just give them a
Shouldn't
break.
judge. Never judge people. Never judge. Hold your judgment.
So now we get into the really fun stuff. We're going to talk about driven oscillations, which is really where the idea of resonance comes in now that we've armed with all the stuff we need. Most systems do have some kind of damping, so that if you set something in oscillation, it'll stop oscillating, right? We don't really know any oscillation that doesn't eventually stop, and that's because of some kind of damping. Comes in lots of different forms depending on the specific kind of oscillation, that dissipates the energy of oscillation and returns the system to its equilibrium state. And we can fight that by feeding the system energy. We can drive it at some frequency, and we don't have to drive it at the natural frequency. We can just simply take a system and make it oscillate at whatever frequency we want. And so these next three slides are kind of important. And I think kind of fun if you think about it. You can do the same thing that I'm doing here yourself with a pendulum. So let's first of all think about a mass on a spring that is driven back and forth at a low frequency. And in particular, I didn't say it here, but I want to be clear that the way I drive it is I'm going to take the free end of the spring. Imagine this spring sitting on a frictionless table for now, or at least a low friction table. I'm going to take the free end of the spring and I'm going to move it to the right. And then I'm going to move it back to the left, and then to the right again, and to the left. Sinusoidally, which is what we mean by driving it at, if I'm going to drive it at some frequency, that means mathematically that I have to actually drive that free end precisely sinusoidally at that frequency. And we could talk about why that is later, but I don't want to talk about it now. If I do that with a mass on a spring at a low enough frequency, all that will happen is the spring will simply do what my hand is doing. The spring is operating essentially like a rod. It's just a rod connected to the spring, to the mass, and it makes the mass do what my hand is doing. Stiffness wins in this case. At low frequencies, stiffness wins, and the result is that the, quote, response amplitude, I really should have put that in quotes, but the response amplitude, the distance that the mass moves through, is the same, or approximately the same at least, as the drive amplitude, and is, quote, in phase with it. When I move my hand to the right, the mass moves to the right, etc. You can try this with a pendulum. Just take a plumb bob, something with a weight on the end, move your hand slowly to the right, and then slowly to the left, and you'll see that the bob does exactly the same thing, as long as you move your hand slowly. And in both cases, it's because stiffness wins. Gravity wins in the case of the pendulum. And the stiffness of the spring wins in the case of the mass on the spring. So before I open that to comment, let's just look at least the next slide, where I now drive the spring at a high frequency. Now I'm going to take the free end of the spring. I'm going to drive it back and forth really, really fast. And I think you can see what happens if I drive it back and forth really, really fast. Of course, when I when I compress the spring toward the mass, that does exert a force on the mass that would like to make it go, to the right. But before it has a chance to, I pulled the spring back, and now the force is the other way. And the result is that the mass basically just sits there. I wouldn't mind if that's all you take away from this, is that the mass just sits there. The response amplitude is nearly zero because inertia wins. The stiffness of the spring is completely irrelevant. You're just moving your hand back and forth. The spring can't do anything to the mass because it doesn't have enough time, given the fact that the mass is what it is. It's too much mass for that spring to do anything. Now, if you look really closely at what's going on, you'll find out that, in fact, even though the response amplitude is nearly zero, it's actually out of phase with the drive. This won't happen immediately. You have to wait for things to come to what's called a steady state. But if I take a mass on a spring and I oscillate my hand back and forth really quickly, and things come into a kind of a steady oscillation mode, what actually happens is that the mass moves toward my hand as my hand is moving toward it, and vice versa. The response now is, quote, out of phase with the drive for that reason. And I think if you think about it, or if you do it with a pendulum, so I said try this with a pendulum, and I think you'll see why that's the case. If you drive the pendulum back and forth really quickly, holding the string, moving it back and forth quickly, you will, I think, kind of see and maybe intuitively understand why the pendulum actually moves not very much at all, but out of phase with the drive. I don't know if that sounds intuitive or not, but I challenge you to give it a try and kind of make it intuitive. And I'll take some questions before we move on to, or comments before we move on to the next slide. We're getting toward the end here. Just a few more things. Okay. Good. Well, then that means, of course, when nobody responds, that means everybody understands. So that's what I take away. I learned that from years and years of teaching. As long as you can get the class never to say anything, it means they all understand it. Oh, Jiwatsi's here. Hiwatsi's here. You got anything, or do you just want to be on stage with the cool kids?
I just wanted to say I don't understand, but I was asleep.
Yeah. Well, that's, of course, the other thing that I learned pretty well in my teaching career as well. Okay. Well, let's move on to slide 11 then. What happens if I drive the mass on a spring near its natural frequency? Well, now the interesting thing is that the oscillation amplitude, the response amplitude, is now large, right? I'm driving it at its natural frequency or near its natural frequency. Now the response amplitude is really large. And the interesting thing is that the response amplitude lags the drive by about and by exactly at the natural frequency a quarter of a cycle. Actually, that wasn't quite. Those of you who really know resonance know that what I just said about exactly isn't actually quite right too. But and I challenge you to do this with a pendulum as well, but I think you can think about it with the mass on the spring. If I'm moving my hand back and forth, left and right like that, right? I'm driving the mass to the right when I'm moving my hand toward it, and then I start pulling my hand back, but it takes a while for the mass to stop moving to the right, and then it does start coming back. And as it's coming back, I start moving my hand toward it again. It takes a while for the mass to stop moving toward my hand and then turns around and moves away. So the response is large and lagging the drive. And it turns out that lag is a quarter of a cycle. In fact, if you look at the response of this mass as a function of the drive frequency, it starts out in that low frequency domain. Amplitude of the response is equal to the amplitude of the drive, in phase. And as I increase the frequency, the response gets larger, slowly larger and larger and larger, and it lags more and more and more until at the natural frequency, I get maximum response and a lag of 1/4 of a cycle. And then as I keep increasing the frequency, the amplitude gets smaller again and continues to lag by more and more until at high frequency it lags by a half of a cycle. That means it's out of phase. And this is a very common thing. You can try this with a pendulum. I think you'll see why that's the case. And then the only question might be, well, what determines that maximum amplitude? And that's where I won't spend much time talking about it here, but that's where the amount of drag comes in. If you have a very low drag system, then the amplitude when you're driving it at the natural frequency will be enormous. On the other hand, if you have a little bit of drag really affects the response when the response is large. And so that's the thing that actually limits how much amplitude you get. Okay, comments on that? All right, once again, everybody's with me. That's great. Um, let's move on to number 12. So here's a more complicated when you have systems composed of many elements, they have lots of normal modes with different natural frequencies. The response will largely look like that of the normal mode that's closest to the driving frequency. You'll usually have something that it's probably close to being in resonance with. And a good example of this is what's called Chladni plates. These are two-dimensional metal. They're just metal plates. Often they're squares, but sometimes they're circles. You can just make a plate in any shape you want and then stimulate it somehow with a drive frequency while you have sand on top of the plate that naturally collects at the nodal lines of that resonant mode. And this is a picture of all sorts of different nodal lines of Chladni plates driven at different frequencies. And you can see the sand collecting along the parts of the plate that don't move. In between those nodal lines, if the plate is moving up on one side of a nodal line, it's moving down on the other side. So you can see all of the different ways, some really interesting patterns that you get. And there's lots of videos of Chladni plates online. There's a good one there that I put, but you can look for videos. You can watch Chladni plate videos all day if you want. What did I want to say about that? Okay, and
So,
then once again,
John,
yeah, go ahead.
a question on the being, what is it, Chladni plates. Do you guys use group theory to figure out like how many notes you're gonna get or how many vibrations you're gonna get and things like that?
Well, I don't know about us guys. I know that I haven't.
Physicists.
Yeah, I actually don't know.
Okay.
There might be. That's a good question. I'm not even sure. When you look at these patterns, I don't know that I would have. I don't know how I would have gone about predicting what those. Some of them I could predict, but there's a lot of them I think I'd have a really hard time predicting. Some of the circles crossing lines. So there's some pretty amazing patterns there.
Yeah.
And of course, the one thing that's true is that the more complicated the pattern of nodes, the higher frequency that thing is going to be because the plate is now oscillating. So up in one part, down in another, very short wavelength if you want, short kind of two-dimensional wavelengths, high frequencies.
But presumably it's symmetrical, so you can determine what the symmetry of
right.
the system is, whether it's
That's
like
where
a
you were
C2
going.
or CS or,
Right. You probably know that stuff a lot better than I do, Sam. But I think you're right. Just the shape of the plate tells you a lot about the symmetries that you'll see. You wouldn't see something that had an elliptical symmetry on a square plate, for instance.
Correct.
Yeah.
Yeah, there are a lot of, you can use group theory to do the frequency and mode. Basically, you're looking at the, if you have a symmetry, there's a degeneracy, meaning that at the same eigen energy, you'll have many modes, many eigenvectors So that you can going from, I mean, basically, yeah, going from the symmetry of the shape, you can deduce the number of degeneracy or number of eigenvectors at the same eigenvalue. That's yeah.
Good.
Uh,
Thanks, Hanson. I didn't realize that you were in the audience. I would have called you up on the group theory question because I figured you would, if anybody in the room knows something like that I don't, you're exactly the guy. So thanks for that.
Welcome. And it's basically it's mostly the group representation theory, the representing the groups in mostly linear space, linear algebra, and transformation. Yeah.
Okay. Yeah. Good. Thanks. So I want to end just with talking about the tides, which is what stimulated this entire bite of physics. I was talking to some people about tides the other day. And I think it's just one of the most wonderful examples of a response, a complicated system responding to a complicated driving force. You could imagine taking, certainly in a bathtub, you can do lots of things. You can kind of swish your hands back and forth at a constant frequency. There'll be a lot of weird stuff happening at first, but after a while, the bathtub will settle up into a response everywhere that's at the same frequency as your drive. And you could maybe figure out what that is if you knew the shape of the walls of the bathtub, how full it is, where you're putting your hands, which way you're moving them, what the frequency is, all that stuff. You could kind of figure that out. The tides are complicated because you have a really complicated system. Oceans of water confined to wildly irregular basin between the continents, etc., driven by an also really complicated force, the gravitational influences of the sun and the moon on the spherical surface of the earth. These are gravitational tidal influences of the sun at different frequencies, the sun and the moon at different frequencies, closely related frequencies, but not identical frequencies. The sun is exerting a tidal force that has has a twice per 24-hour period to it. Now, technically speaking, it's really once per 12 hours because the tidal influence on the second part of that 12 hours isn't identical to the tidal influence on the first part. But at least to a first approximation, I can just think of it as being two cycles of gravitational influence per 24 hours. And for the moon, more like twice per 23 hours because the moon moves about an hour's worth away from the sun every day. That's, more or less. Sometimes those two drives are in phase, just like any two frequencies that are close but not identical, like the left turn signals on the two cars ahead of you in the left turn lane, which go in and out of phase. Sometimes they're out of phase. And it takes a little over a week to go from the in phase to out of phase condition. So, in a sense, what the driving force of the tides looks like is a 24-ish hour cycle, really more like 23-hour-ish, because the moon's tidal influence is twice as big as the sun's. So it's more like the moon's driving frequency twice per 23 hours that's modulated, meaning that the amplitude of that drive force is small, and then a week later it's large, and then a week later it's small again, a little more than a week, and so on. So complicated driving force. But it is a driving force that at least, in some sense kind of repeats. It doesn't exactly repeat even. So it's complicated that way too. But that driving force, at least to a first effect, you can kind of think about it that way. So what does the response look like? Well, this is what you see. Slide 14 is what you often see in textbooks. It's absolutely not what happens. Anybody who tells you the tides look like this is just wrong. The idea being, I should point out that if you just think about it, slide 14 is probably a good way for me to think about this. It is the case that either the sun or the moon pulling on the earth creates a tidal effect. The tidal effect, or I should say the tidal force, is such as to pull the ocean away from the Earth on the sunward side or the moonward side, and to pull the Earth away from the ocean on the anti-sunward or moonward side. So the drawings that show these two lobes like this light blue lobe around the Earth itself, is a nice representation of the driving force, but it's not a drawing of the response. The oceans don't do this. If they did, then everywhere on Earth we would have a big tidal wave of water washing over us twice a day. It doesn't do that because the oceans are confined to basins. And so the response of this complicated system to this complicated, but maybe not quite as complicated driving force is what's shown on the final slide. And the way to really look at it is, if you want to explore this further, you should look into and then make a part of your vocabulary amphidromic points. This is a diagram of the oceans showing the amplitude of the response. The color gives you the amplitude of the response as a function of position. And once again, this is kind of a generic thing. It's not always this amplitude. The amplitude changes over time. The phase of the driving force never exactly repeats, but comes close to. So this is a pretty good representation of the tides. It shows the amplitude of the tides as a function of position in the ocean, and it shows you that there are these places called amphidromic points that effectively have little or no tidal effect at all. There's really nothing going on at an amphidromic point. And what happens at each amphidromic point, there is a high tide line that goes through that amphidromic point and a low tide line that goes through that amphidromic point at 90 degrees to the high tide line. And then there's other lines if you want. And those lines rotate around the amphidromic point either in the clockwise or counterclockwise direction. So if you take the amphidromic point off the west coast of the United States, the lines of high tide and low tide and tides in between rotate, in that case, counterclockwise around that amphidromic point. So when the high tide sweeps up the west coast of North America, it sweeps up the west coast, we get our high tides in Los Angeles a little bit before Andy gets his high tides up in the Bay Area, and a little more before they see them in Seattle, and a little more before they see them up in the Gulf of Alaska, etc. And then that high tide line sweeps around, goes through the North Pacific, sweeps down through the south, and comes back around 24 hours later, 23 hours later, I should say, to sweep up the west coast again. Meanwhile, the other side of that high tide line swept up in the 12 hours between those two, or the 11 and a half hours between the two. And also the low tide line swept up. So we've got low tides line passing through the amphidromic point, a high tide line sweeping through the amphidromic point, all tides in between, and then all of them rotating around that point. It's a weird response, right? It's not at all like the textbook picture. Yeah, go ahead.
Yeah. Actually, it's because it's pushed by the Coriolis force. The wave is pushed by the Coriolis force against the coastline, so it sweeps around the coastline. That's.
I'm not sure I buy that. Do you know? That may be right, but the problem, of course, is nothing is really moving. I don't.
Yeah. But the thing is, the wave itself is moving, but the water stays the same. But the just like the tidal force is the tidal wave is moving around because of the gravitational differential, right? And then when the moon and sun changes position, the tidal wave changes, but the water stays the same. So in this case, it's the same effect. The Coriolis force pushes the wave around, but then the wave actually hits the coastline. And then but the coastline, the soil and then rocks are stationary, and then it reflects on, the wave kind of reflects off of the coastline, but it goes along the coastline tangentially.
Well, I
And
think you'll have to color me a little skeptical yet, even though I know that you have often been right about things that I was skeptical about. I am still a little skeptical. I'm looking at the directions of motion around these amphidromic points, and there does look to be a kind of a correlation, but I don't think there's an exact correlation with hemisphere, for instance. And I don't think the problem is that to create the high tide, you have water kind of sweeping in from many directions. So I'm not sure I see how the
yeah, because
Coriolis.
it's in the basin. It's a kind of a bay, enclosed bay.
Well, okay, I see
And
that. Certainly when it's in like a Bay of Fundy kind of a situation, right?
yeah, so then the Coriolis, let's say, if it moves towards the right, when the wave comes into the bay, then the Coriolis force, let's say, for example, pushes to the right. But
Mm-hmm.
then because of the basin, it pushes to the right. Then you have to, at the end, you have to hit the coastline, right? So when you have a circular coastline, let's say simplify just call it circle, right? And the coastline is
Like the
circle.
Gulf of Alaska.
Yeah, let's say, and then you pushes against the periphery of the circle, and then it when you move it to the right and it hits the circle, it has to you have to force the trajectory in a counterclockwise direction, right? And then if you the Coriolis force pushes to the left, then it hits the left side of the circle and then moves in the clockwise direction.
Well, let me
So
just.
so so if you're in a right northern hemisphere and the the southern hemisphere, and depending on which way the mouth of the bay is, you can actually predict which way it's going is going.
Yeah, I think there's some truth to that. I think I'm a little skeptical that it's the primary thing going on. Like in the case of the Bay of Fundy, you would certainly have the same fundamental effect without so and I did want to point out that the nice thing is in a case like the Bay of Fundy, the fundamental thing that's going on is simply that there is a tidal taken as its own little entity. The Bay of Fundy is a body of water that has a driving force in the form of water at its mouth at the southern end of it, going up and down at just the same rate that it takes a wave to move into the Bay of Fundy, reflect off the far side, and come back out again. So the driving force is tuned, that kind of twice per 23-hour thing is kind of tuned to the natural sloshing frequency of the bay. And I think the same thing can kind of be said for the Gulf of Alaska. It's a much bigger area, but it also has a bigger driving force in the form of the how big the mouth is there. So you get these massive tides in the Pacific Northwest because of that same kind of effect. And I'm not sure I buy yet that the Coriolis force has to do with that. Now, it may have something to do with the rotation of the amphidromic points, but I don't see quite enough consistency to make me think that's what's going on. At least around the equator, it's not clear how you decide what they do. But at
Yeah, I
any
mean,
rate, but
yeah,
let me
yeah,
just finish
sure.
this up, and then we can start the discussion. The point really to make here is that this is an example of a complicated system with a complicated driving force that ends up coming into a really interesting mode because of the complicated boundary conditions of the system and the complications of the driving Actually, it's not so much because of the complications. We'd get pretty much the same thing with just one of either the moon or the sun. Presumably, we get kind of the same thing. But I'm done, and we can talk more about this business, Hanson, or whatever anybody wants to talk about.
Yeah, just want to make a short addition. So it also depends on the shape of the channel or the bay. If it is a long, narrow channel, and then the water comes in through the mouth, then it's mostly kind of sloshing, going from the end to the from the mouth to the end and then back. But if it is a circular, then you have but actually, if it's a long channel, then you have, depending on the wavelength, you either have a standing wave or you have a different running wave. And then, but if it is a circular shaped basin, then you'll have basically a low point, which is most what we call it amphidromic point, and then the water just goes around the edge. Yeah, just want to add that. We can look at the the different examples of the geological kind of shape of the different basins and see whether the theory applies.
Yeah, the thing I say all the time, and I think this is true, that one certainly has made. I think people have made numerical models, kind of finite element models of the oceans, and then subjected them to the tidal forces. And I think, but I say without actual knowledge, I would be very surprised if they haven't reproduced to a pretty good degree the kind of things that we actually see experimentally. This data, I assume, in this diagram is experimental data, but I'd be pretty surprised if finite element models don't yield the same results just simply by applying the actual Newtonian, and that's all you need here is Newtonian physics to do the calculation. Anybody else have anything to comment on resonance or anything else? We didn't talk about resonance in electric circuits. I kind of tantalized Benjamin. Tantalated, is that a word? Tantalized Benjamin with a comment earlier. And we don't have to talk about that. I'm not particularly eager to. Oh, we are joined by Abaya. Is that right? Anyway, did you have something? And how do you say your name?
Yeah, Abayadas. Yeah,
Okay.
Abayadas. So yeah, I wanted to speak about this. So, I mean, I have some comments on it too because there's a whole field of EMC, electromagnetic compatibility, and how it resonates with electric circuits and the resonance aspects of things. So one thing I wanted to talk about, one thing I thought about as I was doing my electrical engineering bachelor's was Moore's law, because Moore's law, it helps. It's the rate at which I guess you could say transistors reduce in size. It's like it gets shorter in duration every time and allows us to make smaller and smaller computing circuits. So in relation to that, and then the applications of physics as it comes to both the observation of what's happening on the Earth on geological scale and other aspects. So it's just like we have a race condition between AI versus and uh, the functioning and the, I guess you could say, the acknowledgement of um, physics studies as it applies to I guess, I don't know, counsel to the government and stuff. So that's what that was in my mind. I just joined the room, so it's a little bit of a broad topic, um, but it makes definitely a subject, a matter of to talk about, um, and that's what I wanted to just say. So yeah, I don't know. I just want to bring that up because I know
Okay.
Google has
Well,
been, yeah.
yeah, I'm not. I guess I'm not completely sure what main point you're trying to make there, at least with regard to resonance. I thought maybe you were going to something like as we make circuits smaller and smaller, there's kind of inherent oscillatory natures that one might expect. And I don't know if this is true. Oscillatory behaviors that at higher and higher frequencies, I don't know if there's a point at which those oscillatory frequencies become problematic because they're interfering with the switching frequencies. Maybe Benjamin knows something about that, but I thought maybe that was where you were going.
Sort of. I mean, in the sense, I just wanted to talk about oscillating frequencies and how it relates to modern day, because whether it be the towers we use for cell phones and how they can be programmed to kind of influence thought patterns or pick up on thought patterns from the cell phones and other
There
devices.
you go. That's the hit you needed.
Well,
Yeah.
I
No,
wondered
the
a little
reason.
bit. There is the whole because the whole
Reciting Moore's
Moore's
law
law
as if
thing.
it were a law. That was the first clue.
Got it.
Getting excited about a talk on resonance. That was the second clue.
Yeah, yeah.
But
Well,
5G.
yeah. There we go.
That's
Icing on the
yeah,
cake. Huh?
yeah.
Yeah. Anyways,
Yeah.
I'm not a physicist, so I don't have my perfect verbiage and everything. But I do.
Oh, you said 5G perfectly right.
Thank you.
Nailed it.
Thank you. No. Yeah. But I do. But I think my whole point of approaching this topic is from a point of both a point of um, efficacy as well as, I guess you could say, proper application, given that life forms within this world are affected by resonant frequencies. So that's the broad topic that I wanted to kind of just touch on. And I'm actually thinking about getting a master's in, not master's, PhD in physics. So I was just wanted to kind of get your guys' opinion on this, because I'm sure there's quite a lot of research papers on this topic itself or pertaining to this type of thought of thing.
Well, I think Benjamin is
Do we
certainly
have
right in pointing
brown
out that.
note in the next 20 seconds here? Is that what's coming?
I'm sorry. Say again, Benjamin.
I just want to predict brown note. It's going to make an introduction.
Yeah,
Next one.
I mean the resonance is just as you said, Benjamin. I agreed. My mind kind of went in the same direction yours was going as well. Uh, not to say we don't welcome interest in resonance of any form, but I think people, non-scientists, do tend to take the resonance ball and run with it in ways that are distinctly non-scientific quite often. And maybe I'll just leave it at that. It did. What did it occur? There was something I was thinking. Uh, oh, now I've lost it. Something I was going to say beyond that. Go ahead, Sam.
So John, I wanted to be a kind of a nitpicky asshole because
All right.
that's who I
That's why you're
am.
on stage, Sam.
Yeah.
Sam is always putting
Dude.
me out of a job. I swear. Like, I can't do anything before Sam jumps in. I will do that. Like,
So just on a very, very small, unimportant point with respect
That's
to
all
the
right. Just lay
string.
it on me, Sam. Come on, just go
Yeah,
ahead.
no.
Smack me in the.
That this is a negative comment against me, not you, because like you talked about all this beautiful stuff, and I'm coming here, but this one little spot, you know. So so that string that you had on the floor, and you said that it's an equilibrium, but and then you used a term that kind of triggered me, which was you said it has some kind of memory that where it was, and it's gonna go back. So I wanted to kind of clarify that and say it doesn't have a memory. What it does have is that, first of all, the most thermodynamically stable position for a string is a straight line, because at that point all the forces cancel each other out. When you have a bend in the spring, one part of it, the inside of the bend, the molecules are closer to each other, and so they repel each other. On the other side, they're far from each other, they don't repel each other as much. So that's why if you put the string on a frictionless surface and come back 3,000 years from now, it's going to be a straight line. And so the memory that you're talking, so the string that's on the floor is in an energetically minimum well, and if you change the position of it, you're going to put it into another minimum. Now the question is the force of friction on the string greater than the internal force of molecular repulsion? If molecular repulsion is greater, the string will then straighten out. If it's less, it'll stay in its position. So the memory that you're talking about is if you take the string from a local minimum and put it in a local minimum that's higher than the local minimum it started out with, it'll rearrange itself to get back to another local minimum.
So
So I hope I was clear on that.
go ahead, Andy.
Well, this is a weirdly favorite subject of mine. If you want to start a great slap fight among sailors or sound engineers, coil their cables or lines wrong, and
Exactly, man. Or
you will find out
musicians. Or
or
musicians.
musicians, I guess. Well, the ones with PhDs in physics, but they people have opinions about this. It's the funniest thing to have an opinion about. But I think what John meant by memory is if you coil a line incorrectly over its life, you will end up getting these twists and stuff in there, and the wire core actually gets twisted outside the shield. And the same thing happens with sailing line. And there's like the right way and the wrong way, and everyone knows exactly what the right way is, and everyone has a different idea what the right way is. But so I think I don't know. It's a funny topic.
So Andy, you're talking about through pressure, you're actually changing the molecular structure of the coil.
Right.
And so now you're creating a whole new set of internal molecular forces, which gives rise to that permanent bend, right?
Right. And in my defense, that's exactly what I was referring to. The memory is a memory of abuse or whatever that has really changed it so that straight is not the configuration it wants to be in.
Yeah. So
Yeah.
you're talking to a scientist who's also a lawyer. So being nitpicky wordsmithing is.
I wanted to also say, I mean, with regard to what Andy was saying, I learned the right way, not in my early days as a yachtsman under my father's tutelage, but when I became a maintenance engineer in a recording studio, and the head maintenance engineer taught me the right way to coil mic cables. Which is underhand, overhand,
Over under.
underhand,
Yeah.
overhand, and if you treat your cables, all my mic cables are wonderful. You can uncoil them and they will lie straight, flat on the ground because they have always been coiled the right way, which really, and it really, whenever I see somebody kind of trying to help me by being a good roadie and coil my cables with the whole around your elbow, through your wrist, around your,
Oh,
I
that's the
just
worst.
cringe. Yeah, it's
Yeah,
horrible.
never. Same thing with electrical cables. Never go around your elbow. Never. That's a
Never.
rookie move.
That is rookie.
But my favorite way is just to let it lie however it lies. Let it do figure eights. Don't even try to fix it. And that way you're not adding any stress that needs to be there. Yeah. In the sailboats, you have the advantage that you can always tie one end off and throw the whole rope and just drag it for a few minutes and then coil it back up, and it's nice and straight. It's hard to
Yeah.
do with that with a mic cable.
Every once in a while, I have an electric leaf blower with a 100-foot light duty electric cable. And I think that when I blow leaves, and I've never figured out exactly what I do, but I think I always end up running around the yard and turning in the same direction. So over time, the electric cable gets all coiled up, and I have to take it off of the leaf blower and then walk down the street, a couple of houses, pulling the cable behind me and trying to kind of, whip it around, get the turns out as much as possible, because I always coil it the right way. But if you're taking a cable that already has turns in it, that coiling it the right way doesn't work so well. You have to kind of do what it wants to do instead of what you want it to do.
you got to do reparative therapy on it first. By the way, I'm back on the topic of resonance. I'm riding my bike right now, and I stopped to talk about coiling cables. But I'm about to ride by the Bay model,
Ah,
which
cool.
is a fantastic visceral visualization of well, the Bay. But it's if anybody's ever in San Francisco Bay Area and Sausalito, and they're interested in tides, definitely stop by the Bay model.
And I want to point out, Andy, that you will be right across the street from where I learned how to coil a cable.
What? Mind blown. Oh yeah. I took a picture of that place last time. Today I'm going to go in front of the Bay model because I wanted to. Just kayak place next door I was going to go to. Carry
Cool.
on. Sorry.
And the correct way to coil a cable, of course, is clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Very close tension.
You know, that's funny. There actually is a difference in how you're supposed to coil most modern line is straight core with a braided sheath, but dock lines and stuff are still coiled. Is that the right? Twisted. And there is a twisted line. You want to do that one direction based on the direction of twist. So it's almost like Coriolis, but not really.
Well, now you're talking Shamash's language, I think. Okay. Yeah, go ahead, Hanson.
Yeah, just want to add one thing because you guys are talking about musical instrument. And also this has to do with, previously the question that Sam asked about the symmetry and degeneracy. So we know the distribution of frequency depends on the geometric shape, geometry of the instrument or the container. But we can also ask the inverse question, whether given the distribution of frequency, can we deduce the shape of the instrument? Actually, that's a pretty famous question. So you can actually look up for, can we hear the shape of the drum? And the answer is actually no. There's also degeneracy in that direction as well. So you can have different shapes of drum, but with the same distribution of the frequency, and which actually the simple case would be you have triangles, right triangles, and then you stack them together, put them together, and then you have the same. However many triangles you put together, you're going to have the same distribution of frequencies. So you cannot tell the shape of the drum. And another, we can talk about that, and then I want to mention another fact about the distribution of frequency. This is the Weil, Hermann Weil's law. Basically, the law says that given a smooth boundary, the domain of smooth boundary, the number of frequency counting the degeneracies would be proportional to the wavelength, to the power of n divided by 2, and then times the volume of the domain. Yeah, I'm done speaking.
Okay, thanks. So yeah, go ahead, Shamash.
I just have a couple of questions. Number one, immediately related to what Hanson was talking about. So we cannot hear the shape of the drum, but can we see from the frequency if you have an oscilloscope, for example, and you have the exact sound waves? Can you see the shape of the drum? Because we are told that these things are unique. You know, there's a whole thing around the Stradivarius violins, and they have a unique timbre to them, etc., etc.
You're talking about whether from the magnitude, relative magnitude
From the shape of the wave itself. So every violin, for example, will give you a different shape because it's made of slightly different material, and so.
Well, for instance, you could the sound waves might, even if the frequencies were the same, the phase relationships might be different. So the sound wave might be different. We wouldn't. I don't. When you say we can't hear it, do you mean there's nothing in the sound wave that reveals what the drum is?
Yeah, I think because basically it has to do with the what do you call the plate, Philly plate? I forgot the name.
Chladni's.
Chladni plate. Basically, you have a standing wave, right? The resonant frequency, and so basically it's our stationary, and it's a question about if you can ask about the magnitude, relative magnitude of the different frequencies, and I don't think you can even see that because with the counterexample of putting the triangles together, I think that you actually these magnitudes are the same.
Oops.
I would think if you could see it somehow on an instrument, then you should be able to hear it. In fact, audiophiles, who are often assholes, will insist that there are lots of things you can hear that you can't measure in any possible way, which seems absurd to me also.
Yeah, that's the thing. So if you take a Stradivarius violin, there's countless studies done on those violins, and they prove that they're not louder than others. They are not more complicated. They don't produce more complicated waves than others. Even if they have more noise than modern violins, but the people still prefer them simply because of what you're talking about. So that because they are like these things, they have a quality that you cannot measure somehow.
Yeah, I mean, I think the shape is just about the boundary, like the domain, this cavity, the boundary of the cavity, and I think people say, I mean, you always have the different signatures, only that you have enough. Lots of instrument or lots of shape to produce different sound profiles or the frequency, basically the frequency distributions. But there are always many cavity shape produce the same frequency distribution.
Hey, I'm just reading some of the chat and learning interesting thing that Wissam did some work with Tom Rossing, who I knew, who was really the master of the physics of music. I mean, he wrote an incredible book on the physics of music. So I'm in awe, Wissam, that you worked and taught with him.
Can I squeeze in one more question, John?
Yeah.
Maybe like much more rudimentary than what we were talking about.
That's probably a good thing. I mean, a little more of the aim of this room, but go ahead.
We've talked about the frequency and about the complications there, but one of the things that always defeats my intuition is that the speed of propagation of a wave in a medium is independent of the amplitude of the frequency, or so we're told. Of course,
it's not quite true, but yeah, pretty true. Yeah.
So
not with water.
Not with water.
Yeah, that's true. That's right. No, that's a really good point. In Andy's case, it's absolutely not true. There are water waves where the amplitude not so much. I mean, amplitude it's still pretty, but there are soliton solutions to wave equations in water where the speed actually depends on the amplitude. Yeah, go ahead.
The
Andy.
wavelength on water waves, so there's a very simple relationship. I forget what it is, but basically longer wavelength waves are faster.
Right, but that's a wavelength.
That's why surfers have to tow into big waves because nobody can paddle that fast, and that's why surfers are surfing massive waves these days. They never did before, is because of they managed to break the speed barrier by using a
Right.
wavelength.
But that is a different thing. As far as amplitude goes, most water waves that we're familiar with, travel essentially independently of amplitude, except for these soliton solutions where the speed actually does depend only on the amplitude. So that's a nonlinear kind of a thing that you get in sometimes called, what are they called? Channel waves or something. Somebody help me. I can't remember what they're called. But you see them, Bohr waves, I guess. They're waves that you'll see in a very long, straight, like concrete line channel. You'll get a wave that moves along, and you'll see many waves, and larger waves will overtake smaller waves and then just keep on moving right through them because they don't combine. It's really an amazing kind of a wave. But the waves that you see out in the ocean, deep water waves and even shallow water waves, have speeds that depend on the wavelength, but don't depend, at least to first order, on the amplitude.
There's a story about a scientist riding a horse and chasing a wave down a canal,
Right.
and because he was like couldn't understand what was going on, and I don't know who that was. Maybe you know the
Yeah.
story, but he discovered this phenomenon. It has to do with the depths and the width, and there's like a resonant. I don't know if it's resonance the right word, but there's a wave that doesn't stop, like it doesn't dissipate, it just keeps going.
Yeah.
I don't know what it's called either.
Tidal bores.
Yeah, the soliton. I mean, like John was saying, it's soliton. Soliton means that it doesn't dissipate, doesn't change, widen the wavelength. It keeps the shape.
Doesn't really have a wavelength. It's just a solitary wave that moves along. Yeah.
Yeah, and it doesn't change shape as it travels.
Yeah, and that was one of the big things at the beginning of all the hoo-ha about nonlinear dynamics. Solitons were a big deal, and a lot of people had hopes in particle physics for solitons and all sorts of things.
Mechanics. I think Klein-Gordon equations has a soliton solution.
I
Okay.
think there's something like that going on in like the Bay of Fundy. Like wherever you have these massive tidal shifts, it's usually because it's down a long channel, and it seems like there's something like that going on. Like the long shape is kind of tuned, and I think it actually slows the tidal wavefront down, and you literally get like people always talk about a tidal wave, and they're usually wrong. There's no such thing as a tidal wave, but in these certain instances, and there's some you can find some videos online where there's like waves going up rivers, like one big whitewater wave, and it'll just go for miles. And it literally is like the tide coming in.
With a height, just a permanent height difference between the front and the back. Yeah.
Yeah, it'll just go for miles, and literally on one side, on the other side of the wave, the water's a foot and a half bigger, or something like that. Like the way, so I think something like that is going on.
Yeah.
With Bay of Fundy too. I'm not sure.
So, John, do you have time for another question, or?
Yeah, sure. I do want to move toward finishing in the next 10 or 15 minutes here.
Okay, so the quick question is, if we in an oscillating system, if we change the weight on one side, right, it's going to slow down the oscillation.
Now, let me understand. Are you thinking about like just two masses connected by two springs or something?
By one spring, right? Well, so you have two masses, you have one spring in between them, and they're oscillating. Now, double the mass on one side, the rate of oscillation is going to go down, right?
Yeah, that's right. But
what happens to the energy of oscillation?
Well, I mean, so the energy of the oscillation just depends on how big the oscillation you make, right? I mean, you can't, if you're going to double the mass, presumably you're going to stop the system, you're going to, and then you're going to set it up again. If you're going to ask something like, well, what happens if you have the same amplitude, but one mass is double what it was before? Well, so first of all, what do you mean by amplitude? Do you mean the distance between? You're going to keep the oscillation, the maximum and minimum distances between the two masses the same? You can't mean that you're going to have both masses going through the same amplitudes they did before, because that's kind of a meaningless thing. They're now one of them. If you go into the center of mass system, which you'd like to, first of all, the center of mass is no longer at the midpoint of the spring. And second of all, the smaller mass will have a larger amplitude of oscillation in that reference frame than the larger mass does, right? The larger mass will move away from the smaller mass. The smaller mass will move further away, depending on the ratio of the masses, so to keep the center of mass where it is. So there's a lot of things in terms of energy. It's a little hard to explain, but the way that's ultimately dealt with is just by converting that system mathematically to one mass on one spring. I think on the spring, the same spring, with the mass
Right.
being now what's called the equivalent mass, and you're probably familiar with that idea.
Yeah. Yeah. Yeah.
Yeah.
Okay. Right. Thanks.
Mm-hmm. Okay. Any other going once, twice, three times? Any other comments? Thanks for coming. Just remind everybody, Sam's going to have, Sam, you want to say again what you're doing on Monday?
So Monday at noon Pacific, 3 Eastern, 9 p.m. European time, I'm gonna have my restart my chemistry series. The first one is just going to be a review of what we're talking about, but then the week after that, I'm going to start with a lecture on quantum mechanics, which basically starts out with the lecture that John gave today.
Great. And Shamash, you want to do a plug for Philosophy Wednesdays?
Sure, as always. Same time as this room, 17:30 GMT, or what is it? 9:30 your time.
Pacific.
Yeah.
12:30 Eastern.
We do a room that is science / math / philosophy of science room. It's called Philosophy Wednesdays. I'll plug in a link in chat. Also, we'll be uploading these episodes with the Bites of Physics, with Sam's series now. They will be all on YouTube on the Scientific Discourse channel, which also will have a link in chat in a minute. Just write Scientific Discourse on YouTube, you'll be able to find it. Last week, we were talking about, in my room, problems and ontology of science. So what is it that we commit that is reality or not? And probably the following week we'll do something very related. I'm still not sure on the topic, but it will be in that field. So yeah, if you're interested,
thanks, Shamash. And one of these days, I'm twisting Andy's arm, Hero, for those of you who don't know him, to do a some kind of a thing that he may do in conjunction. With what's his name? No, I'm not. I'm blanking. At any rate, Andy does lidar work, and I think it's really interesting stuff, used in I think in driving Teslas and all sorts of things. What you can do with lidar. So I'm kind of hoping to twist his arm and get him to do
Tesla
one.
don't use lidar.
Sorry.
Teslas don't use lidar.
They don't use lidar. Okay, so I could. Yeah.
No, Elon Musk has kind of really famously made a point about not using lidar on Tesla.
So what do Teslas use for their auto detect capabilities?
He relies a lot on cameras.
It's just cameras. Is that right? I didn't know that. Okay, interesting. Well, at any rate, so he's not going to talk about Teslas. He's going to talk about lidar.
But I think that Tesla also uses radar.
Oh, well, now you're just making it complicated. It's got something against lidar.
Wait. Have we met?
I don't think so. I mean, they considered using lidar and radar, but they settled on using camera only.
Seems like what we do when we drive cars. It seems like a reasonable thing. Anyway,
that's exactly the point.
Okay. So anyway, thanks for everybody for coming. Presumably see you next week. I don't know what that topic will be yet. I almost never do until the day or two before, but we will see you then, and enjoy a little gravity on the way out. We'll have a tidal interlude after my gravity song. this song.